Oh, you guys, here we go. Beginning up with this lecture series, we're in chapter 18, section 18.1. I'm going to start with some general hygiene practices here. My computer said it had a virus, and so I'm taking extra precautions here. Okay, with that said, here we go. Guys, if you remember last time, we had a lab. It was called the Black Magic Lab. And we were looking at some things called the reaction rates. We were varying the concentration, we were varying the temperature, and we had a catalyst. If you remember, things that are very concentrated, the reactions tend to go faster. If it's dilute, it tends to go slower. Temperature. If you increase the temperature, you increase the speed of things. You increase the rate of the reaction. We're also going to be talking about catalysts. So these are some of the things we're going to be taking a look at. We're looking at reaction rates. So we're picking up on that lab that we did. So the first thing that we're going to be taking a look at is called the collision theory. So here's the collision theory. And the concept of the collision theory is that your reactants must collide in order to make the products. Let me give you an example. Imagine that you have hydrogen and you have oxygen. So you have H2 and you have O2. Let's go ahead and create this so that it's balanced. We're going to have 2 hydrogens and 1 oxygen. We're going to create some water here. And we create H2O. We create 2 waters from this. If we do a little drawing of this, what the hydrogen is this is what the hydrogen looks like. We've got 2 hydrogens and we have 1 oxygen. If you draw the end product over here, you have 2 waters that look like this. Well, my starting stuff, which is, these are my reactants, this is very different than my ending stuff, which is my products. If you take a look at this, these guys are completely separate from this, and then they are attached. So in order for chemical reactions to take place, they have to collide with each other. That's the collision theory. So the collision theory is that your reactants, and your reactants, again, this is your starting stuff, must collide to make the products. To make the product or products. And again, your products, this is your ending stuff. So here's your reactants here. Here is your products. Okay? So imagine that I have some pieces of Play-Doh, and I want them to form a new chemical compound. Okay? I want them to collide. Boom. Oh, they just collided. Boom. Oh, they just collided again. Okay? Boom. This is collide. Okay, this is kind of fun. But back to this. However, collision alone is not enough. We need to have what's called activation energy. So if I have these 2 things, just by them colliding does not make them connect with each other. What do I have to do? I have to take these and kind of smash them like that. Now they're actually a new compound, but I had to add this extra energy for that to happen. And that is called the activation energy. So the activation energy, this is the energy that's added to make a reaction happen. So I'm just going to say energy is going to be E. The energy added to make a reaction happen. Okay, well, I have a little candle here, okay, and I'm going to take a match. Okay, inside this candle is lots of energy. It's waiting to be released. And if I strike this match will probably go out in a few seconds, but if I light the candle's going to last for at least an hour. Well, why is that? This has lots of energy that's stored on the inside of it, and that energy is going to be released. So the total sum of the energy that's going to be released is a lot more from this candle compared to with this match right here. However, I have to release that energy. I have to have it activated. So what I'm going to do is we're going to now light this candle. Okay, we'll put the match out. So now the energy is being released from this candle. And again, the amount of energy released over this next hour will be very, very high, but it needed that initial impulse of energy to make this actually happen. So we'll put that aside, we'll bring that back later. So it's the energy added to make a reaction happen. So if you just have collisions is just not enough. So if you imagine the two pieces of Play-Doh, and I'm going to draw them with dotted lines coming in like this. Dotted lines coming in like this. What happens is they're going to hit each other, and then they are going to then bounce off of each other. Okay, that's because there wasn't enough energy, there wasn't enough force to push these guys together. However, remember when I smashed them with my hands, that was enough energy to make the reaction happen. So sometimes reactions, they need a little bit of extra input energy, and that's the activation energy, the energy added to make a reaction happen. So this right here, this would be an example of low energy. Let's take a look example of high energy. If you take these things coming in, and I'm drawing the arrows solid now, representing that they're coming in a lot faster. These guys have high energy, and the end result of that will be they will stick together. So there's two types of reactions. You may have recalled these from previous science classes. Energy can either come out, or you might actually have to have energy come in. So I have two examples of reactions. We have an exothermic and we have an endothermic reaction. So here I have a sample, and this is a sample of calcium chloride. So if you can see, the temperature of this is about 20 degrees Celsius. It's close to room temperature. And what I'm going to do is I'm going to add a little bit of water, and then I'm going to stir with the thermometer. Stir, 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 stir. Okay. Take a look at the thermometer now. If you guys are able to see that, it's actually already at 30. Stir, stir, stir. Stir, stir, stir. Okay, take a look at now. The temperature is at 40 and rising. So a lot of heat is coming out of that. That would be an example of an exothermic reaction. So therm means temperature, like the thermostat. In the room, you want the temperature to stay the same, so you set your thermostat. So therm means heat or temperature. So therm means heat, and exo is like exiting. Heat's coming out. Heat's coming out of the reaction. The thermometer is able to detect that and respond to that, and so heat's going to be coming out. So with an exothermic reaction, heat is going to be released. And if you feel the bottom of the flask, what that entails is that it's going to feel warmer. Or we'll just say it feels hot. Let me go and get the other one over here. This is ammonium chloride. And just to show you, I'm starting again at room temperature, so we're at 20. I'm going to add some water. Now, this is actually not chemical reactions that are taking place. This is just for it to dissolve. There's no chemical reactions again. So I'm going to stir, 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 stir. And we can see what from 20 all the way down to 10. Stir, 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 stir. A little more. And maybe that's about it. Okay, but you can see the temperature, it did go down. That's an endothermic reaction. So again, therm means heat, endo means in. So An endothermic reaction is the opposite of an exothermic reaction. Exothermic means heat's being released. With an endothermic reaction, for it to take place, is heat is needed. Heat is needed for this to take place. And if you feel that, of course, it's down to 10 degrees Celsius. Yep, it's about 10 degrees Celsius still. This is going to feel cold. So it feels cold. So we can have heat going in or heat coming out. Again, heat being released, it's going to feel warmer. The endothermic is a little bit more tricky. The heat is actually pulled into the reaction, so the surrounding water is going to feel colder as a result of that. With this next section, we have the reaction rates. This is the Black Magic Lab, and the reaction rates are totally dependent upon the speed of the reaction. So let's take a look at this process right here. If you increase the temperature, so we're going to increase the temperature, and what's going to happen to the speed of the particles? You can go ahead and answer. The speed is going to increase. You increase the kinetic energy of those particles, okay? So now, what's going to happen to the number of collisions? They're going faster. You're going to increase the number of collisions. Okay, increase temperature, you increase the speed. You increase the collisions, what's going to happen is you're going to increase the rate of reaction or increase the reaction rate. Why we're going to increase the reaction rate? Well, let's take a look at the collision theory. In order for to create new chemical compounds, they have to collide. Well, if they're colliding faster, you're going to increase the rate at which they form those new molecules. So we're going to be increasing the reaction rate. And when you increase the reaction rate, that means you're going to decrease the time, as we did in our lab. This means that it's going to be going faster. We also did it on concentration. The higher concentration reacted a lot faster than the slower one. So you guys have seen this before, and this is hydrogen peroxide. And I'm going to get a sample of some manganese dioxide. This is a black powder that causes the hydrogen peroxide to fall apart. I have my little scooper here. You see a little scooper? It's kind of cute. Okay, let me go ahead and get this substance. And I just need about the size of a grain of rice. And okay, you can kind of see down there something's going on. Okay, it was bubbling a little bit. But now what I'm going to do is I'm going to bring in the heavy-duty hydrogen peroxide. This is about 10 times as concentrated. Again, I'm going to put in my 1 scoop and we'll see what happens here. And it is bubbling a lot faster. I'm keeping this small scale because I don't want it to explode on my ceiling again. Okay, kind of smells, so we're gonna put it over there. So, I don't know if you can hear it, but it's still reacting over there. So, the concentration, if you increase the concentration, you're going to increase the number of particles. So, just a quick review of concentrated versus dilute. Concentrated means that you have more particles per volume in your solution. Dilute means you have a lot more water, so you're going to have fewer particles in your solution. So what's going to happen to the collisions if you increase the number of particles? Well, if you increase the number of particles, what's going to happen is you're going to increase the collisions. And if you increase the collisions, you're going to increase the reaction rate. That's going to go a lot faster. It's still reacting. Whoa. Okay. It's quite hot. over there too. Okay, and a catalyst. We talked about catalysts during the Black Magic Lab, and this is taking a look at what's happening right now in the previous example with the two hydrogen peroxides. So we have hydrogen peroxide, and hydrogen peroxide naturally breaks down, decomposes, this is one of the classic 5 reactions, into water, H2O, and oxygen. So to balance this out, this is what it looks like. Whoa, just lost the lights. Okay, back here. Okay, so, and, oh boy, oh no, oh no. Chemical reaction taking place, whoa! That was not intended. Okay, back here. I will clean that up a little bit later. At least it didn't hit my ceiling this time. Okay, so what causes this reaction to take place? Well, this naturally occurs if you have light. Light will naturally break down hydrogen peroxide. The hydrogen peroxide will break down into water and oxygen, and that's why the hydrogen peroxide is sold in these containers, because we don't want a photochemical reaction. So light will naturally do this. And if it actually did it on the inside of this bottle, it would be causing oxygen gas to be produced, and that reaction that you just saw right there would take place on the inside of the bottle. It would probably build up enough pressure, and it would probably be a little bomb and explode. So light will cause this reaction to happen very, very slowly. Also, this takes place inside your blood. You have a natural catalyst called an enzyme, and the enzyme breaks down this molecule into these, and it's inside your blood, and that molecule will chop it up into smaller pieces, and when it does so, it's going to release the oxygen bubbles, and that's what happens when you get that on your skin or on a cut. So the last one we did is manganese dioxide, MnO2. Okay, this is a catalyst. It causes this reaction. That was that black powder that I added. And what does a catalyst do? A catalyst, what it does is it lowers the activation energy. So it lowers the activation energy. If you can imagine, the activation energy is what's needed to make the reaction go forward. It's like pushing a ball up a hill. Okay. So here's the activation energy. We're pushing this ball up like this, okay? And when we finally reach the top, it's going to roll down, and then your energy will then be released. So this hill is your activation energy. What a catalyst does is it makes this hill a little bit lower. So instead of pushing it up the big hill, letting it roll down, you don't have to push it up a very big hill in order to accomplish your feat. So catalysts like the manganese dioxide, it lowers this hill, it lowers the activation energy, and your reaction takes place a lot faster.